Welcome to the Enthalpy Change screencast. Enthalpy change is also known as heat of reaction. This screencast provides information on enthalpy change, which is also compiled as a handout here. This is the one-page handout. It's available within Sakai. Please have your periodic table of elements available and your periodic chart of ions. I keep these available on my desk. There's very little information on my desk other than these handouts and a book. This information, which is a handout, I keep as an icon or a shortcut on my computer desktop. Enthalpy change, which is delta H, is the difference in energy between a reaction's products and the reactants, which is represented by this equation right here. And it notes that it's under a constant pressure. And all that means is enthalpy is energy plus pressure times volume. The reason we use the delta H, which is the change, is it's hard to measure these quantities here. So if we ignore them, then we are left with just the change in energy. And that's a little easier to measure, and that's why we use the term delta H. And it's just a difference between the enthalpy of the products minus the reactants under constant pressure. What this all translates to is these two items. Reactants plus heat yield products, and reactants yield products plus heat. When the change is positive, it means energy is flowing into the reaction. When the change is negative, it means heat flows out of the reaction. The easiest way to determine whether the enthalpy is positive or negative is see which side of the reaction it's on. If it's on the left, it's positive. If it's on the right, it's negative. If it flows out of the reaction, it's always negative. If it flows into the reaction, it's always positive. We'll look at a couple of examples of this. In review, here are some symbols that we use for chemical equations. We've already used the delta or change symbol, and it just means the reactants are heated, as in this equation. Solid gallium and oxygen gas are heated to form gallium-3 oxide. While we were reviewing specific heat, we used the term heat, which we refer to as Q, and heat is also energy, and specific heat is, of course, heat divided by mass times the change in temperature. So delta was change, and that was just the final minus the initial, which is very similar to enthalpy, products minus reactants. Let's take a look at enthalpy. If the products contain less energy than the reactants, heat is absorbed, and the change is called endothermic. Endothermic means into, and it's best remembered using this endoskeleton of a horse, means the skeleton is on the inside, and that just means right here that heat is on the left, as we discussed, and it's just called endothermic, which means heat is absorbed. And an excellent example of this are these cold packs right here. When the chemical reaction occurs, it absorbs heat. Here is another explanation of exothermic, or the explanation of exothermic. And on the right here, we have a thermite reaction, which is exothermic. It means it gives off heat quite spectacularly, and we'll talk about this right now. If the products contain more energy than reactants, heat is released, as we are viewing on this paused video here, and the change is called exothermic. Here's an example of an exothermic skeleton. It means on the outside, that's a lobster. And simply the reaction exothermic means heat is released or flows out of the reaction. Let's take a look at this thermite reaction here. And we know from the past that These are the reactants on the left. These are the products on the right. Since heat is on the right, it means it's a negative value always. Negative joules. As we look at the numbers here, we see that Fe2O3, which is just simply iron oxide, and that's just rust, combined with 2 moles of aluminum to yield 2 moles of iron plus aluminum oxide and heat. So, when combining these items, a lot of heat is produced. On this slide, it says that an enthalpy change of reaction is known, and once it's known, the reverse reaction's enthalpy is also known. So all we do is change the sign. That means 2SO3 plus heat yields 2S plus 3O2 is an endothermic reaction, and to write it as an exothermic reaction, all I have to do is go reverse the reaction, which is 2S plus 3O2 yields 2SO3 plus heat. And by definition, since heat is on the right, it is negative. Since heat is on the left here, it is positive, and it can be expressed with actual values here, which are joules. So even though I express heat positive here, it could be represented with a negative 790 kilojoules, and on the left, it would be the opposite value. Let's look at this table here, and we'll look at it in detail a little bit. Here's the first part of the table on the left, endothermics, or endothermic reactions, meaning heat is absorbed, common in cooking eggs, evaporating water, melting ice cubes, and photosynthesis. Heat is a reactant. It means it specifically is on this side of the equation. It's a positive sign. Let's take a look at this decomposition equation here. And we see that this molecule, which is simply phosphorus pentachloride, has heat added to the reaction to decompose into these two simpler molecules. So there we are again. Phosphorus pentachloride plus heat yields phosphorus trichloride and then chlorine gas. And actually all of these are gases. And you can see how this more complex molecule is broken down into these simpler molecules. And it says here on the right, delta H is 67 kilojoules, which is not very much energy, is added on the reactant side of the equation. And since it's added here, it's decomposed into these two molecules. Next, let's look at an exothermic reaction, meaning heat is released. And we'll look at a favorite reaction, which is water. And we talked about this earlier. Exothermic reactions include burning sugar, nuclear fission, making ice cubes, combustion of fuels, and heat's a product. So we have two molecules, or they could also be compounds, combining to form something else. And then heat is released, and we know it's released because it's a negative sign. Here we happen to have two of these molecules of hydrogen. So there would actually be two of these rotating around, combining with one molecule of oxygen. And we saw that in the Zeppelin burning, where we had hydrogen, which would be a big combination of hydrogen or supply, burning in the atmosphere, which would be air, and it yielded a lot of heat, which is this much bigger number than we just saw, and some water. And that's what's shown right here. Here's our table displayed again. If delta H is positive, it's endothermic. If it's negative, it's exothermic. And you can review that on the handout. Thank you for watching this screencast.